Hello everyone. Vehicle modeling process should be a building block approach, starting from a simple system to a complex one. Creating a suspension subsystem is the first step to build a full vehicle model. It is highly recommended that the vehicle system should be verified at each step from the very first stage of building suspension models. A half-car model has a vehicle body constrained to the ground. In most cases, the half-car model demonstrates the quasi-static behaviors of the suspension. Wheels and tire patch forces generate the suspension kinematics, compliance, and component load. A steering system and a stabilizer bar give more information about steering kinematics, compliance, steering load, and vehicle roll. One of my favorite stops is to apply the huge force at wheel center and tire patches. You can easily figure out load paths graphically. Excessive deformation at suspension attachment due to improper bushing representation can be easily detected. Don't forget to turn force and moment graphics on. Once each subsystem model is built and validated good, we are ready to build a full vehicle using the subsystems. This slide shows a subsystem list of passenger vehicles of sedans or SUVs. A minimum set of subsystems for a full vehicle model is front and rear suspensions, steering, and wheels and tires. Vehicle dynamics model should have enough details to answer questions that the analysis is expected to give. A simple bicycle model cannot answer overall steer ratio, vehicle roll characteristic, suspension component load, and embodied structure sensitivity to NVH performance. A simple vehicle body model could be a rigid body of mass, CG, and moment of inertia. The body also can be high-fidelity FE models to represent the compliances as well as inertia properties. Passenger and luggage mass should also be comprehended in the full vehicle with a vehicle ballast. As complexity of the model goes up, more detailed physical representation of subsystems is integrated to the full vehicle model. Flexible bodies better represent the load paths and compliances in the vehicle system. The powertrain enables simulations for several vehicle performance issues of durability and NVH. The driveline model of half shaft and prop shaft can give insight for driveline-related NVH performances. They should be included to answer driveline-related questions about half shaft vibrations and power hop. Simple tires could be replaced with the high-fidelity commercial tires for nonlinear handling, rough road simulation, and rim ground-out conditions. The vehicle mass, inertia, center of gravity, and trim heights also affect the vehicle performances substantially in some cases, thus should be carefully modeled. A takeaway from this slide is that the fidelity of a full vehicle model is associated with the questions asked for virtual simulations. A full vehicle model has a few ballast conditions to remember. The first one is curb mass, where no passengers and no luggages are included. In this ballast, the fuel and windshield wiper fluid are fully loaded. EPA certified mass is for EPA tests, where the driver and front passengers are on board. Vehicle performance tests are run at this ballast. In some cases, 2 passengers are replaced with the driver and instrumentation at the front passenger seat. Gross vehicle weight, GVW, is fully loaded with full passengers and luggage. Gross axle weight rating, GAWR, is the maximum allowable axle load while maintaining GVW. This is the mass for suspension load generation. In low-frequency vehicle ride, the sprung mass has about 1 to 1.5 Hz vibration frequency, and wheel and tire assembly has 10 to 12 Hz hopping vibration. The unsprung mass is the key to accurately calculate the wheel hopping frequency. A 150 pounds lumped mass is attached to the passenger's hip point, H point at each seat. The rated cargo is attached to cargo area. The vehicle CG is a critical parameter in vehicle model. X and Y coordinate of CG are easily calculated from the vehicle corner masses. However, the CG height is not easily available. Historical data would help to assume the CG height in early vehicle development stages. Suspension hardpoints are defined at the curb ballast. Since hardpoints from the CAD files have no preloads, there would be slightly discrepancies between a CAD and a multi-body model loaded at curb. Adding more ballast means the vehicle height changes, the vehicle sitting lower. The vehicle trim height is a distance measured from the ground to the point in the vehicle. The wheel housing opening is a good point to measure, which is easily accessible. The body rocker location, jack installation location to speak, is also good for trim height measurement. The trim heights from the wheel housing opening and a body rocker have the effect of tire radius change. It would give substantially different numbers on hot summer afternoon and in chilly early morning. To eliminate the tire radius effect, more accurate trim height can be measured from a vertical distance from two suspension points. An example is a bottom point from the front cradle and the bottom of the lower ball joint. The trim height varies with the spring preload or check load, but it should satisfy the plus minus 10 mm tolerance. Suspension engineers predict the spring load at curb position and share them with the spring suppliers. Trim height data should always go with the corner masses. Sometimes, trim height correlation did not make sense due to mass numbers from poorly calibrated scales. The first data set to build a suspension model with is suspension hardpoint. They are key locations representing vehicle suspension. The table on the right-hand side shows hardpoint from an SLA suspension. The vehicle reference frame has aft plus X, right plus Y, and up plus Z direction. The hardpoint data comes from vehicle CAD models. These are not constant but change as design gets mature per packaging, vehicle dynamics, suspension design perspectives. The hardpoints are captured at curb ballast. Hardpoint not only positions joints and bushings, but also specify their orientations using axial reference point. The LCA picture in the slide demonstrates that the position alone cannot describe the LCA and its attachment to the suspension properly. Please note that the front and rear wheel would not have the same Z coordinate. This means that the ground line is not parallel to x-axis, which may mistakenly calculate the cast angle.